In this lecture, we're going to talk about chemical reactions, and in particular discuss chemical reaction stoichiometry, how we determine excess and limiting reactants, and then introduce the concept of extent of reaction. The reason we're doing this is that we're going to be performing mass balances for reactive systems. If reactions occur, constraints exist on the relative flows of reactants and products, and we can no longer set input is equal to output in all cases. We will be able to do this if we talk about the total amount of mass that comes in and out, but we won't be able to do this if we're talking about the mass of a particular component. The stoichiometry of a chemical reaction indicates the relative number of moles of reactant consumed and product produced. In order to determine the stoichiometry, we first write the chemical reaction as a list of the reactants on the left-hand side of an arrow, and on the right-hand side of the arrow, a list of the products. In this particular example, hydrogen sulfide reacts with oxygen to produce sulfur dioxide and water. This reaction, as currently written, is not balanced. It does not indicate the relative number of moles of reactant consumed and product produced. Because if we look at the number of atoms of oxygen that are present in the reactants on the left-hand side, there are 2. But if we look at the number of atoms of oxygen that are present in the products on the right-hand side, there's 3. For this reaction to be balanced and therefore indicate the relative number of moles of the reactant consumed and product produced, the number of atoms of oxygen on the left have to be equal to the number of atoms of oxygen on the right. The same is true for hydrogen and sulfur. In order to balance this chemical reaction, what we'll do is we'll assign arbitrary values for coefficients in front of each of the species that participate. So we have an A to represent the number of moles of hydrogen sulfide that will participate in the reaction. B represents the moles of oxygen. C represents the moles of SO2 produced. And D represent the moles of water that's produced. To determine these coefficients, what we're going to do is set equal the number of atoms of each of the atomic species that are present, hydrogen, sulfur, and oxygen. We're going to set the number of atoms that participate as reactants equal to the number of atoms that appear in the products. Before doing that, we can arbitrarily set one of these coefficients to 1. In this case, we're going to set the coefficient for hydrogen sulfide to 1. The stoichiometric coefficients are represented by the Greek letter nu. And the subscript of nu indicates the species for which it applies. In this case, H2S indicates hydrogen sulfide. If we equate the number of atoms of hydrogen that are present on the left-hand side of the chemical reaction, which are the hydrogen atoms that are present in the reactants, we see that there are 2. We'll take the number of atoms in hydrogen sulfide, which is 2, and multiply it by the value of A, which is 1, to get 2. There's no hydrogen present in the oxygen, so we don't add anything to the 2. We set this equal to the number of atoms of hydrogen that are present on the right-hand side in the products. There's no hydrogen present in the sulfur dioxide, but there are 2 atoms of hydrogen in water, which we'll multiply by D in order to set the total number of atoms of hydrogen in the reactants equal to the total number of atoms of hydrogen in the products. This gives us an equation for D we can solve, and we find that D is 1. This is a stoichiometric coefficient for water. If we do the same thing for sulfur, there's 1 sulfur atom in hydrogen sulfide. We multiply that by the stoichiometric coefficient of sulfur, of hydrogen sulfide, which is 1. That's the number of atoms that are in the reactants. We set that equal to the atoms in the product. Sulfur is only present in SO2. There's 1 atom, and we multiply that by the coefficient C to get C on the right-hand side of the equal sign. Solving this equation, this trivial equation, we find that C is equal to 1, and that's the stoichiometric coefficient for sulfur dioxide. The balance we're going to do for oxygen is a little more complex. If we look at the right-hand side, or left-hand side for the reactants, what we see is that there are 2 atoms of oxygen in each molecule of oxygen, and therefore the number of atoms that participate is going to be 2 times B, the stoichiometric coefficient for the oxygen molecule. We're going to set that equal to the oxygen that appears in the products. We have 2 atoms that are present in each molecule of sulfur dioxide, so multiply 2 times C to get the amount of oxygen that appears in that particular product. And we're going to add to it the amount of oxygen that's in the water, which is going to be the coefficient of oxygen, which is 1 in water, times D. Since we know C and D, we can calculate B. And we find that B is 3 over 2, 1.5. That's a coefficient, stoichiometric coefficient for oxygen. Note that if we have a set of stoichiometric coefficients for a chemical reaction, in this case we determined that the coefficient, we set arbitrarily the coefficient for hydrogen sulfide to 1. We calculated that the value for oxygen is 3/2, for sulfur dioxide is 1, and water is 1, from balancing the atoms of hydrogen, sulfur, and oxygen in the reactants with those in the products. If we take this equation and multiply all the coefficients by 2, we end up with the coefficients of 2, 3, 2, and 2. This is the equivalent representation of the stoichiometry of the reaction. Ratios of stoichiometric coefficients allow us to determine the amount of a chemical species that's either produced or consumed given an amount of another chemical species present in that participates in the reaction. So for instance, we want to take the ratio of the stoichiometric coefficient for sulfur dioxide to the stoichiometric coefficient for hydrogen sulfide. It would be 1 over 1, which is 1. This ratio is used to calculate relative amounts of species that are consumed or produced. So for instance, if 2 moles of water are produced, we can ask how many moles of hydrogen sulfide are consumed. And we can calculate that by taking the 2 moles of water that are produced and multiplying by the ratio of stoichiometric coefficients from our chemical reaction. That there's 1 mole of hydrogen sulfide consumed per mole of water that's produced, and therefore 2 moles of hydrogen sulfide would be consumed. Let's try this calculation again. Let's suppose that 6 moles of sulfur dioxide are produced. How many moles of oxygen are consumed? Why don't you take a moment and see if you can do this yourself. The way we would do this is we would take the amount of sulfur dioxide that's produced, 6 moles, and multiply it by the ratio of stoichiometric coefficients for sulfur dioxide and oxygen. We know that there's 1.5 or 3/2 moles of oxygen that are consumed per mole of sulfur dioxide that's produced. So if we multiply 3/2 times 6, we end up with a value of 9 moles of oxygen are consumed. When we talk about chemical reactions, there's some jargon that we'll use. The first is stoichiometric proportion. If 2 reactants are present in the same ratio in a feed as the ratio of their stoichiometric coefficients in the chemical reaction that occurs, we'll say that those 2 reactants are in stoichiometric proportion. Usually, 2 reactants are not present in stoichiometric proportion. There's an excess of one or another. The limiting reactant is the first reactant to react completely if the reaction were to proceed to completion, if we were to try to consume all the reactants. The excess reactants are those that are left after the limiting reactant is consumed. And we're going to go through a couple examples of this, several examples of this. For instance, let's go back and look at that sample reaction in which hydrogen sulfide reacts with oxygen to produce sulfur dioxide and water. And we're going to use as the stoichiometric coefficients 2, 3, 2, and 2. So we avoided having a stoichiometric coefficient that's a fraction. We would get the same result if we were to use the other set of stoichiometric coefficients. But this is a little bit easier to work with. So for instance, if 4 moles of hydrogen sulfide are present in a feed along with 6 moles of oxygen, are these 2 reactants in stoichiometric proportion, or which one is in excess, and which one is limiting? The way we can answer that question is to take the ratio of the number of moles in the feed. There's 4 moles of H2S, there's 6 moles of oxygen, so we'll take that ratio as 4 over 6, which is 2 over 3. And let's compare that then to the ratio of the stoichiometric coefficients. The stoichiometric coefficient for hydrogen sulfide is 2, the stoichiometric coefficient for oxygen is 3. We find is that the ratio of the moles of the reactants in our feed is exactly equal to the ratio of stoichiometric coefficients. Therefore, those 2 reactants are in stoichiometric proportion. Now let's assume that there are 10 moles of hydrogen sulfide present and 12 moles of oxygen present. The ratio of the number of moles of the two species that are present is 10 over 12. If we compare that to the ratio of stoichiometric coefficients for hydrogen sulfide and oxygen, we see that that ratio is 2 over 3, or if we multiply both the numerator and denominator by 4, that's 8 over 12. What this indicates is that if 12 moles of oxygen are present, we only need 8 for the two to be in stoichiometric proportion. We actually have 10. What this says is that H2S is in excess. It's greater than the amount that's required for the two reactants to be in stoichiometric proportion. H2 is in excess. We also say that oxygen is limiting. Because if we look at the amount of oxygen that's required for complete conversion of the H2S that's present, we take the 10 moles of H2S that are present and multiply the ratio of stoichiometric coefficients in order to get the amount of oxygen that's required. If we multiply it by the ratio of 3 over 2, the stoichiometric coefficient for oxygen divided by the stoichiometric coefficient for hydrogen sulfide, we get 15. To completely react the 10 moles of hydrogen sulfide, we need 15 moles of oxygen. However, we only have 12 present. This is why oxygen is limiting. When we have an excess amount of one reactant, we often will be asked to calculate the fractional excess or the percent excess. The way we do that is we take the amount that's present, in this case for hydrogen sulfide is 10, and subtract from it the amount that would be required to completely react with the limiting reactant. That's the amount that would be in stoichiometric proportion to the limiting reactant. In this case, we know the amount of hydrogen sulfide that's in stoichiometric proportion is 8. That's the amount that would completely react with the 12 moles of oxygen that's present. We subtract these two and divide by the amount that's required for complete conversion of the limiting reactant, oxygen. So in this case, we'll take the difference between 10 and 8, which is 2, and divide by the 8 moles of hydrogen sulfide that would be required to react with the 12 moles of oxygen present. We get a value of 0.25. That's a fractional excess. If we multiply by 100, we get the percent excess, which is 25. If all the oxygen were to react, we would say that the conversion of oxygen, which is the ratio of the moles that react divided by the moles fed, would be 12 over 12. If all that were to react, we'd have a fractional conversion of 1, and the percent conversion would be 100, 1 times 100. There's a fairly simple way to determine the limiting reactant by simply comparing the number of moles of the reactant that are fed to the reactor, the ratio of the number of moles of two reactants fed to a reactor, to their stoichiometric coefficients. This little table down here illustrates that. So for instance, if the moles of reactant A that are fed to this reactor divided by the moles of reactant B is equal to the ratio of stoichiometric coefficients, the nu for A and the nu for B, the reactants are in stoichiometric ratio, and they would both completely react. There would be no excess or limiting reactant in this case. If the number of moles of A divided by the moles of B is greater than the ratio of stoichiometric coefficient, then we'll say A is in excess. More moles of A are present than are required to react with all of the B that's present. If the ratio of the moles of A to B is less than the ratio of the stoichiometric coefficients, we'll say B is in excess. There's more moles of B present than are needed to completely react with all the moles of A. Let's use what we just learned to determine the limiting reactant for the same reaction that we've been examining thus far, in which hydrogen sulfide and oxygen react to produce sulfur dioxide and water. For this case, let's assume that we have 20 moles of hydrogen sulfide and 28 moles of oxygen fed to the reactor, which is a limiting reactant now. The way we do this is we'll compare the ratio of the moles of H2S to the moles of oxygen that are fed. That ratio is 20 to 28, which has a numerical value of 0.714. We'll compare that to the ratio of stoichiometric coefficients for hydrogen sulfide and oxygen. That ratio is 2 to 3, which has a numerical value of 0.667. Since the ratio of the moles fed is greater than the ratio of the stoichiometric coefficients, we conclude that oxygen is limiting, and hydrogen sulfide is in excess. We want to calculate the amount that hydrogen sulfide is in excess, and to do that we need to know the amount of hydrogen sulfide that's in stoichiometric proportion, stoichiometric ratio with the limiting reactant. The amount of H2S that's in stoichiometric proportion to oxygen, the limiting reactant, is given by the amount of oxygen that's present, 28, times the ratio of the stoichiometric coefficient for hydrogen sulfide, which is 2, divided by the stoichiometric coefficient for oxygen, which is 3. If we multiply that out, we find that the amount of H2S in stoichiometric proportion to the 28 moles of oxygen fed to the reactor is 18.7. The amount of H2S fed is 20, so it's clearly in excess. To calculate percent excess, we take the amount fed, 20, subtract the amount that's in stoichiometric proportion to the limiting reactant, 18.7, divide that by the stoichiometric amount, 18.7, and multiply by 100. Doing that, we find a value of 7.14%. Another concept that will be useful in analyzing processes that have chemical reaction that help us perform the mass balances for these processes is something called the extent of reaction. The extent of reaction is represented by the Greek letter xi. Xi is defined to be the moles consumed or produced of a species I divided by the stoichiometric coefficient for that species I. Or we can rearrange it to say that the moles consumed or produced of I is going to be equal to the product of the extent of reaction, xi, times the stoichiometric coefficient for species I, nu sub I. What's interesting and what makes this concept of extent of reaction useful is that xi is the same for each reactant and product. I'll try to prove that here to you in this little table. Xi is defined to be the moles of I that are consumed or produced in the chemical reaction divided by a stoichiometric coefficient. We take this and split this out, put the moles of I over here in this table and the stoichiometric coefficient down here, then multiply top and bottom by the moles of J. We know that the moles of I that will react with a given number of moles of J is equal to the ratio of the stoichiometric coefficients, nu I over nu J. If we plug in those stoichiometric coefficients, we find is that the nu I in the numerator will cancel the nu I in the denominator, so this reduces to moles of J over the stoichiometric coefficient for J, which we said is the definition of xi. So what we've done is just prove that the moles of J that react divided by the stoichiometric coefficient for species J, or are consumed, is equal to the moles of I that react or consumed divided by the stoichiometric coefficient for that species. So the xi is the very same for all species. The way we're going to use this is that we're going to say if there is n sub I 0 moles fed to a reactor, the number of moles that exit n sub I is given by n sub I is equal to the amount that enters plus or minus the extent of reaction xi times the stoichiometric coefficient. We'll use a plus if the species I is a product, and we'll use a minus if the species I is a reactant. Let's use this concept of extent of reaction to determine the limiting reactant for the very same problem we looked at using the ratio of the stoichiometric coefficients. If 20 moles of hydrogen sulfide and 28 moles of oxygen are fed to a reactor, what's the limiting reactant? We can determine which one's limiting by calculating the value of xi, the extent of reaction that would be required for complete consumption of each of these species. What is the value of xi required for complete consumption of hydrogen sulfide? And compare that to the value of xi for complete consumption of oxygen. If we use the definition of xi and how we calculate the amount of a species that exits from the amount that enters, we'll be able to determine which reactant is limiting. So for instance, let's look at hydrogen sulfide. The amount that exits is going to be the amount that enters minus, in this case because it's a reactant, the stoichiometric coefficient for hydrogen sulfide 2 times the extent of reaction. If we set this equal to 0, knowing that the amount that enters is 20, we can calculate a value for xi. Xi is 10. The extent of reaction would be 10 for complete consumption of hydrogen sulfide. Let's compare that to the value of xi we compute for complete consumption of oxygen. The amount of oxygen that exits is the amount that enters, minus the stoichiometric coefficient for oxygen, which is 3, times the extent of reaction. Once again, the minus sign is here because oxygen is a reactant. If it was a product, we'd use a plus. We plug in the amount of oxygen that enters, which is 28, and subtract 3 times xi from that, and set that equal to 0, we can calculate the extent of reaction required for complete consumption of oxygen. The extent of reaction then is given by 9.33. Since the reaction extent for complete consumption of oxygen is less than the reaction extent for complete consumption of hydrogen sulfide, we say that oxygen is limiting. And the stoichiometric amount that H2S that would be required to react is just given by 2 times the value of Xi for complete consumption of oxygen, which is 9.33. And we just talked about how we looked at this using the ratio of the stoichiometric coefficients. And we can compute the percent excess hydrogen sulfide in exactly the same way. We take the amount that's fed, subtract off the amount that would be in stoichiometric proportion that would lead to complete consumption of the oxygen that's fed. Then we divide that by the stoichiometric amount and multiply by 100. The answer is 7.14%. Let's compute what leaves a reactor if there are no products present initially and 50% of the H2S that's fed to the reactor reacts. If, for the case we just looked at, in which we had 20 moles of H2S fed and 28 moles of oxygen fed. If 50% of the H2S fed reacts, the amount that reacts is given by 2 times Xi. That's going to be equal to 50% that's fed, so 50% would be 0.5 times 20. So if we set 2 Xi equal to half of 20, which is 10, we find that the extent of reaction would be 5 for complete, or for 50% consumption of the H2S that's fed. We can calculate the number of moles of H2S that exits from the definition of Xi in this equation for the amount that exits the reactor. The amount of H2S that exits is the amount that enters. We'll use a minus because it's a reactant. The stoichiometric coefficient for H2S, which is 2, times the extent of reaction. Plug in the numbers, 20 entered. We subtract off 2 times the extent of reaction, which is 5. 20 minus this product, which is 10, leaves 10. And we repeat this for each of the other species in this reaction. For oxygen, the amount that leaves is the amount that enters. A minus because it's a reactant. The stoichiometric coefficient for oxygen, which is 3, times the extent of reaction Xi. Plugging in the numbers, we had 28 that enters. We're going to subtract off 3 times the extent of reaction, which we set as 5. So we perform the math here. We end up with 13 that exits. Let's look at the sulfur dioxide. The amount that exits is the amount that enters, which is 0. We're going to assume that there's no products present in the feed. Now we're going to add to it 2 times Xi, the stoichiometric coefficient for sulfur dioxide times the extent of reaction. The plus is because this is a product. Plugging in numbers, we get 0 plus 2 times 5, which is 10. The same thing, we're going to do the same thing for water. The amount that exits the reactor is the amount that enters, plus, because it's a product, the stoichiometric coefficient for water, which is 2, times the extent of reaction. We plug in the numbers, we have 0 that enters, plus 2 times the extent of reaction, which is 5, gives us a value of 10. And we can calculate the total number of moles by summing up that exit the reactor, by summing up the moles of each of the species. 10 plus 13 plus 10 plus 10, we get 43. And we can compute the mole fraction of hydrogen sulfide in the product stream by taking the ratio of the moles of hydrogen sulfide in the product to the total number of moles. That's 0.23. That's also equal to the mole fraction of sulfur dioxide and water, because both exit, the exit amount of flow rate of these two is both 10, the same as the hydrogen sulfide. The mole fraction of water can be given by 1 minus 3 times this. There's 3 species have this mole fraction, or we can simply take the amount that exits, which is 13, and divide by the total amount, which is 43. We're going to conclude this lecture with an example in which we go through a series of calculations for a chemical reaction involving balancing the equation through determining the limiting reactant. The problem we're going to look at, this example problem, is one in which acetylene, which is C2H2 with a molecular weight of 26, is hydrogenated to ethane, C2H6, molecular weight of 30, in a reactor. And we're told the feed contains 1.5 moles of hydrogen per mole of acetylene. First off, we're going to balance the chemical reaction. The reaction is acetylene reacts with hydrogen to give ethane. We'll put unknown coefficients, A, B, and C, in front of each of the species. We can arbitrarily set one of them to 1, and we're going to set A to 1. So this equation becomes acetylene plus B hydrogen gives us C ethane. Now, if we balance the number of carbon atoms that are on both sides of the equation, we find that there are 2 carbon atoms associated with the acetylene. We're going to set that equal to 2 times C, which is the carbon atoms associated with the ethane product. Doing that, we find the value of C is 1. Now, if we balance hydrogen, there are 2 hydrogens for each acetylene, so it'll be 2 times 1, the coefficient for acetylene. And we're going to add to it the number of atoms of hydrogen associated with the hydrogen molecule times the coefficient for the hydrogen molecule, which is B. So we have the amount of hydrogen atoms in the reactants is 2 plus 2B. We'll set that to the hydrogen that's in the products, which is just going to be the value of C, which is 1, times the number of hydrogen atoms in the species, which is 6. We can solve this to find B is equal to 2. Now, the balanced chemical reaction is given by 1 acetylene reacts with 2 hydrogen to give 1 ethane. Next, let's calculate the stoichiometric reactant ratio of hydrogen to acetylene. From a balanced chemical reaction, we can readily calculate that. The stoichiometric reactant ratio is given by the ratio of the stoichiometric coefficients. So we take the stoichiometric coefficient for hydrogen, divide that by the stoichiometric coefficient for acetylene. We get 2 over 1, which is 2. Now we're going to determine the limiting reactant and the percent excess for the other reactant. The chemical reaction we're considering here, the hydrogenation of acetylene to ethane, is reproduced. And what we're going to do is that we're going to assume they have 1 mole of acetylene fed, and because we're given the ratio is 1.5 moles of hydrogen per mole of acetylene, that means 1.5 moles of hydrogen would also be fed. And we'll compare the ratio of the feed rates to the stoichiometric coefficient ratio. So 1.5 moles of hydrogen per mole of acetylene. We'll compare that to the stoichiometric coefficient for hydrogen, which is 2, to the stoichiometric coefficient for acetylene, which is 1. What we find is that the ratio of the feed rates is less than the ratio of the stoichiometric coefficients. What this implies is that the acetylene is in excess and the hydrogen is limiting. In order to determine the percent excess of acetylene, we have to determine the amount of acetylene that would be consumed if all of the hydrogen were consumed, if all the limiting reactant were consumed. The way we do that is we take the amount of the limiting reactant that is fed, 1.5 moles of hydrogen, and multiply that by the ratio of the stoichiometric coefficient for acetylene to that for hydrogen. The stoichiometric coefficient for acetylene is 1, the coefficient for hydrogen is 2. We multiply this out. We find is that the amount of acetylene that reacts with all the hydrogen that's fed would be 0.75 moles. This is the amount that would be in stoichiometric proportion to the hydrogen in the feed. And this is less than the actual amount, which is 1, which is why the acetylene is in excess. To compute the percent excess, we take the amount that's fed, subtract off the stoichiometric amount, and divide by the stoichiometric amount. Multiply all of that by 100 to get a percent, and we find that the acetylene is in excess by 33.3%. Finally, what we're going to do is we're going to calculate the mass feed rate of hydrogen that's required to produce 4 million metric tons of ethane per year. We're going to assume the process operates 24 hours a day, 300 days per year. Now note that 1 metric ton is equal to 1,000 kilograms. The chemical reaction is written out here again. And the thought process for this is that we're going to convert the ethane mass flow rate to a molar flow rate. And then we're going to determine the number of moles of hydrogen that are required from the stoichiometry of the equation, the chemical reaction. Then we'll convert the moles of hydrogen to mass. That's the thought process. Let's plug some numbers in. We're told that there's 4,004,E6 metric tons of ethane per year that are fed. If I multiply this by 1,000, that will give us the number of kilograms per year. We know that from the molecular weight of ethane that 1 mole of ethane is equivalent to 1 kmol of ethane is equivalent to 30 kilograms. This product gives us the number of moles of ethane that are flowing out of this process. To convert the moles of hydrogen that are required, we multiply by the ratio of the stoichiometric coefficients for hydrogen to the stoichiometric coefficient for ethane. The stoichiometric coefficient for hydrogen is 2. The stoichiometric coefficient for ethane is 1. This product then of the first 3 terms gives us the molar flow rate of hydrogen that's required. To convert the molar flow rate to a mass flow rate, we multiply by the molecular weight of hydrogen. We know there's 2 kilograms of hydrogen per kmol of hydrogen from knowing that molecular weight. Finally, we're going to convert years to seconds in order to get a value in kilograms per second. And in this case, 1 year is equivalent to 2.59 times 10 to the 7th seconds. And that's because we're told that this 1 year that we're considering consists of 300 days, not 365 days. And for each of those 300 days, we're going to run the process for 24 hours per day, which is 300, then there's 3,600 seconds per hour. So we multiply this all out, we find that for the 1 year as defined here, the number of seconds in that year is 2.59 times 10 to the 7th. So we'll multiply by the ratio of 1 year is equal to 2.59 times 10 to the 7th seconds to give us a total mass flow rate of hydrogen of 20.6 kilograms per second.